Welcome back. So now we're going to talk about hypothesis testing through simulation with a couple new examples, but I want to remind you of some key concepts here. Alpha is the number that we use to describe the threshold of significance for any hypothesis test. It's basically how credulous or incredulous you are, how skeptical or unskeptical, gullible you are. Alpha equals 0.05 is a standard value of alpha that's used in a lot of scientific applications. Basically, what alpha is telling us is how improbable do things really have to get for you to say, hey, that is not a coincidence, there must be something going on. Now, closely related to alpha is the p-value. The p-value is a measurement of how crazy the results are. If the null hypothesis were true and no effect were going on and really nothing real was happening here, how wild would our results be compared to our expectations if there were no actual effect going on? If the effect is really strong, then the p-value is going to be really low because that's going to indicate that's not at all likely if the null hypothesis is true. So the p-value is actually the probability that we would get results like ours or even more extreme, given that the null hypothesis is actually the true explanation for things. So these are some key concepts used in almost every hypothesis test. Now, let's look to our new example for the day. So hypothesis testing by simulation, we're going to consider a political polling example. 1,000 Americans are surveyed, and 53% of them favor X. I don't know what X is. It could be a candidate, it could be a policy. For this example, it doesn't make any difference. But 53% of Americans surveyed favor X. So the question is, perhaps you're writing an article and you want to report the results of this. Is it fair to report that more than half of Americans favor X? It might sound like it's a slam dunk, 53%, that's more than half. So there you go, write your article and claim that it's true. Well, but wait a minute, more than half of those surveyed favor the policy. Is it so much more than half that we can confidently say that more than half of Americans favor that policy? Well, let's see. We have a hypothesis here. The hypothesis, which is called the alternative hypothesis, which is the main working hypothesis of this study, is that more than half of the Americans favor the policy. So I'm going to phrase that by saying P greater than 0.5. P is the population-wide proportion of Americans who favor the policy. So P is going to be the proportion in favor. And this is basically saying population-wide, more than half of Americans favor X, whatever it is. Whenever we're doing any hypothesis test, we need to clarify what the null hypothesis is. The null hypothesis is a statement of equality, parity, no effect, nothing going on here. In this case, it contradicts the inequality of the alternative hypothesis and states that, in fact, exactly half of Americans favor X, whatever X is. So basically, we're juggling two possible explanations in our head here for this 53% figure. The first explanation is that that is a reflection of the reality that more than half of Americans actually favor this. And so when we surveyed Americans, more than half of them said, yeah, that's what I want, right? Another explanation for this 53% is that in fact, exactly half of Americans favor X, whatever it is. In fact, it's evenly split 50-50. But even though our method was not biased, we just kind of accidentally got a few extra on this side instead of that side, just because of the randomness of our phone calls, the randomness of our survey. So basically, the null hypothesis is saying, yeah, it's 53%, but that's really just random kind of noise. Actually, 50% overall in the population is the right explanation. And this is high just because of some random noise, right? Even if 50% of the population favors X, and you do a survey of 1,000, you don't expect to get exactly 500, right? You'll expect some natural variability there, and that's kind of the point. So H0 is possible. It is a possible explanation. The null hypothesis is a possible explanation. So in order to do a hypothesis test, we need to decide up front, well, how credible are we, right? How much are we really going to believe or disbelieve? And so a standard threshold of significance, that's going to be 0.05. Let's just take that as our threshold of significance. Let's say that if these results are that surprising or more so, then we will disbelieve the null hypothesis and say there's really something going on. But if those results are unsurprising on the basis of this standard, then we will say, gosh, I don't really know. Both hypotheses are credible. We need to calculate a p-value. How are we going to calculate a p-value? This is the hardest thing to do in any hypothesis test, is actually do the math and get the p-value. What we're doing here is we're doing a hypothesis test by simulation. There are other ways to get this p-value using standard error and normal approximations, and there are very good ways that use actually a lot less computer stuff and more mathematics. But we're going to use this simple structure of simulation in order to do this one. So we need to calculate the p-value. Let's look to what the p-value is. The p-value is the probability of getting results like ours, or even more extreme, if the null hypothesis were actually the correct explanation. So what we need to do is we need to put ourselves into the mindset of saying, okay, the null hypothesis is right, and we're going to reason about what would happen if it were right. Now, if the null hypothesis is the actual truth in the matter, then when we surveyed 1,000 Americans, each one of them was going to respond yes or no with a probability exactly on the nose 50%, if the null hypothesis is true. And that means that each one of these phone calls is effectively a coin flip, right? You're basically reaching out into a population that is exactly evenly split 50-50 and saying, what's your opinion? And you're going to get a yes or no. It's basically a coin flip. So that means that if the null hypothesis is the right explanation, then what we have done here, surveying 1,000 Americans, is effectively 1,000 coin flips. And so to resimulate this experiment under the presumption of the null hypothesis, which is that out there Americans generally really are evenly split, all we need to do is flip 1,000 coins. Well, we don't have to do it physically, but we just need to flip 1,000 coins. So to resimulate the experiment, assuming assuming the null hypothesis, H0, just flip 1,000 coins. And then we just need to count the heads. Now, of course, I don't really mean that we would literally in the physical world flip 1,000 coins, but we could certainly program a computer to make 1,000 random choices, random yes/no choices with probability 50%. And that's not so hard to do. So we would program a computer to flip 1,000 virtual coins, and then we would count how many times the heads showed up. That would resimulate the experiment, and that would give us a result. We would expect a result around 500, but we would not always expect it to be exactly 500, right? A few more than 500, a few less than 500 would be a natural outcome to this process. We would expect some variability. How much variability would we expect is really difficult to anticipate, but we will see that there is some math to predict that. Resimulating the experiment once is not sufficient to tell us, look, is this really a realistic estimate or not? If we simulate the experiment once and we get, for example, 510 heads for a total percentage of 51% from that 1,000, well, we won't really know, well, like, could we have gotten 53%? Is 53% likely? How likely is numbers like 53%? Just resimulating the experiment once doesn't really give us very much information about how we should read this 53%. But if we flip 1,000 coins and do that, that is, flip 1,000 coins, do that 10,000 times. So just to clarify here, there are 10 million coins going on, right? So we are flipping 1,000 coins and counting the number of heads, and then doing that again and again and again and again and again. And we'll do that 10,000 times. So we're really going to get some broad experience with what happens when you flip 1,000 coins. So you really get some experience, and then you keep track of every one of these. And then we need to ask ourselves the critical question here: how many results out of these 10,000 experiments are over 530? Or let me say, to be specific, how many results are greater than or equal to 550? Why is this the key question to ask? Because The actual measurement that we got was 53%, which is 530 out of 1,000 people. And what we're really asking is, how likely is that in the case of the null hypothesis? So what we do is we pretend the null hypothesis is true, which makes the experiment simply a coin flip experiment with 1,000 coins. We count how many heads there are. We do that 10,000 times, and sometimes we will get 53%. We will get 530 heads. Sometimes we will get 50%. Sometimes we'll get 49%. Sometimes we'll get 530 heads, and sometimes we won't. And if we want to know how likely it is to get 530 or more heads, then all we have to do is simulate this experiment 10,000 times, and then count up how often we get 530 heads or more. Why did I do it 10,000 times? That's kind of an arbitrary number. A computer can easily do this 10,000 times. If I choose 100 billion times, then it's going to have to take the computer a long, long time to resimulate this. So it's kind of like a big number that's not too big for the computer to just crank fairly quickly, and that's kind of an arbitrary number. So we're gonna produce a broad experience with simulations of this experiment under the presumption that the null hypothesis is true, and then we're going to count them up. And I won't bore you with the details of the programming, but I did that before the lecture. And here's what happened. I got 271 times 530 or more. So 271 results, that is out of 10,000, were 530 or higher. And with the results of that experiment, we can estimate and we can deduce the probability of getting results as wonky as ours if the null hypothesis were true, because this is a null hypothesis experiment and we're just counting how often we get results like ours. And how often is it? It's 271 out of 10,000. So 271 out of 10,000, which is 0.027. So as a percentage, that would be 2.7%. So what happened was, after all of this simulation, 2.7% of the time, even when the null hypothesis was true, this random surveying experiment actually did give us results like 53%. Now we have to say, is 2.7% like so crazy out of whack that we think that's not plausible? Like 2.7% is pretty small, but it's not ridiculously small. It's not like winning the lottery kind of odds. It's small, but it's not crazy small. So now we have an important judgment to make. The judgment is this so rare that we will say to ourselves, gosh, that can't be a coincidence? Or is this so common that we'll say, whatever, that could happen, I don't know, right? So that's like how we have to resolve this hypothesis depends on that response. And if you were listening carefully, we decided this up front. We decided this up front when we decided that we would take alpha equals 0.05, which is the standard value of the threshold of significance, as our value. That is the level of rarity in these results that we will regard as so rare it can't be a coincidence. And now this 2.7% or 0.027 is even more rare than that. And so this will justify us saying, gosh, that can't be the result. That can't be a coincidence. So here, this is the p-value. The p-value is less than the alpha value. And so what we're going to say is basically, that's so rare, that can't be a coincidence. We're going to say, gosh, I don't believe that that would happen by accident. I believe that, in fact, there is really something going on here. It's not an accident. The null hypothesis is not credible. And so let's draw a conclusion from this. So let's see. I'm going to erase this stuff, and then I'm going to declare what is an appropriate conclusion from all of this simulated experimentation. So the appropriate conclusion is the p-value. So p-value equals 0.027. P is less than alpha, which is 0.05. And so the appropriate thing to do is we reject the null hypothesis, which is what we usually want to do in any statistical study, in any hypothesis test. Usually what we're aiming at is the rejection of the null hypothesis, which knocks down our main counterpoint, our main contestant here competing against the alternative hypothesis, which we respect as true. And so we say we have statistically significant evidence of HA. And what does HA say? It says more than half of Americans favor whatever policy this is. As a perfectly responsible reporter, we should not report with confidence that exactly 53% of Americans favor this policy, because we don't know that it's exactly 53%, because there may be some randomness in this result. Maybe it's 52, maybe it's 54 out there, generally the population proportion, but we can confidently assert that more than half of Americans favor the policy, because we can reject the null hypothesis on the grounds that these results would be very, very rare if the null hypothesis were true. So that's an example of how we assess a hypothesis test by a simulating experiment. Now, I'd like to give you homework to do this at home, but unless you have 10,000 coins lying around and a lot of time to flip them all so many times, right? Unless you have all this money lying around and you can flip these coins for days and days and days, this is not something that we ever do by hand, right? We program a computer to just simulate this experiment, and then we wait for the results, and the results come in, and then we make our conclusions. But even computers are more and more powerful, and so this technique of simulation is more and more used in the practice of statistics. But it's not the only way to do it, and I want to emphasize that there are ways to do this that are much less computer intensive and based on the mathematics of the normal distribution, which are equally powerful and will give you comparable results here. Okay, we're going to do another example next. And it's another hypothesis test in which we claim that one thing is greater than another thing. So let me write out the setup for the next hypothesis test. This one, I think when I introduced this one, I was feeling a little bit cheeky because I was thinking about chess and I was thinking about trash talking about chess. And so I introduced this example. So the hypothesis that we're trying to test here is the hypothesis that I'm better than you at chess, okay? Which, you know, since it's a wide audience, is probably true in many cases and false in some cases too. So the hypothesis here is I'm better at chess. Now, that doesn't sound very mathematical, but it is. It really is. The hypothesis is that the probability that I would win a chess game is greater than 50%. That is against a particular opponent. So the probability is greater than 0.5. Now, let's say we collect a little bit of evidence, right? How do you assess whether somebody's better at chess? Well, you play some chess games, right? Let's suppose that we collect a little bit of data. So what would the data look like? We might play, say, 9 games. And so I have to make up some numbers here. And since I have the luxury of being the one making up the numbers, I'm going to make them up so that they look good for me. So let's say, for the sake of argument, so let's say we do that, and I win 7. Now, the first thing you might notice about this is that this is a really rather small sample, right? 9 games only. We called 1,000 Americans in the last example, and now we've only played 9 games. But you know what? It's not practical to play 1,000 chess games against one opponent. Like, nobody's going to have that kind of stamina. So it kind of makes sense that this would be a small sample. And now I've chosen these numbers so that it's not intuitively clear whether we have strong evidence for the hypothesis or not. I think when I look at these numbers, I think, well, it was only 9 games, and 9 is a pretty small sample. But on the other hand, I won 7 out of 9 games, which is pretty compelling. And so, like, seems pretty good. So it's not quite clear intuitively whether this is strong evidence in favor of the claim or weak evidence in favor of the claim. And that's what the job of the hypothesis test is. When we look at the evidence, we're not supposed to just sort of eyeball it and say, looks good to me. That's not how statistics works. We're supposed to figure out whether it is statistically significant using this machinery of alphas and p-values. So let's again agree, and we should do this before the analysis and probably, before even we carry out the experiment and collect the data. Let's agree what our threshold of significance is. There is a standard, alpha equals 0.05. Let's say that's going to be our threshold of significance. If the data comes up so that, wow, it's really striking, and it wouldn't even happen with a probability of 0.05, then we will say, wow, that can't be a coincidence. And if the data comes up so that we would say, well, with probability 0.25, say, that could just happen randomly. If it turns out that way, then we'll say, well, that might just be a coincidence. I don't know. So agreeing up front on the threshold of significance will help us not have a whole lot of debate at the end. And that's the responsible scientific way to do it. So let's agree up front that alpha for this experiment is going to be 0.05. And whenever we get our p-value, we're going to compare it to that. Okay, this is a pretty standard choice, right? So let's say I win 7. So how do we do this? Let's clarify what our hypotheses are. The alternative hypothesis is that the probability of winning is going to be greater than 0.5. That is, I'm better, so I'm more likely to win. Now, if anybody out there actually does play chess, then you'll realize that especially at the higher levels of chess, it's not just winning and losing, right? Drawing is a very common outcome in chess. And in fact, you sometimes have chess tournaments where 2 people will play and it's just a draw, a draw, a draw, a draw, a draw. Now, I don't want 3 possible outcomes here because it complicates the mathematics and it complicates the statistics too. So let's just pretend for the sake of argument that a chess game is always either won or lost, right? No 3 outcomes, it's always just win or lose. So just to simplify how the math works. So we have an alternative hypothesis that the probability of winning is greater than 0.5. And then we have a null hypothesis. And the null hypothesis in this case, if you've been paying attention, you will recognize the null hypothesis does not say that you are better at chess. That would be the opposite hypothesis. The null hypothesis says that we are equally matched. So the null hypothesis says we are equally matched. And that means that p is actually exactly equal to 0.05. Sorry, I said that wrong. 0.5, 1/2, 50%. Okay, so that's the alternative hypothesis and the null hypothesis. We have to clarify those to figure out what's going on. Now we're going to resimulate this experiment. We're going to do that in an effort to get the p-value. Now, what is the p-value? I can't say this enough. You really need to understand what a p-value is. The p-value is the chances of getting results like this, or even more compelling, if the null hypothesis were in fact the right explanation. So let's put ourselves, you have to get your head into the mindset of the null hypothesis and really sort of hypothetically believe in it for a short time. And you have to say, okay, the players are equally matched. So if we are equally matched, then just like the political polling, every game is a coin flip, right? Excluding draws for simplicity. If we are equally matched, then every game is a coin flip. And so we can simulate this again, even though it's a completely different situation, we can simulate it with coin flips. So what do we need to do? We have to perform, so let me title this first. So the simulation to get the p-value is, what do we have to do? We have to perform 9 coin flips, and we have to count the heads, right? So that's equivalent to just randomly assigning the outcomes to 9 independent chess games. So we're just going to do that, 9 coin flips, and we're going to count the heads. But this thing is just one simulation of this little tournament that we're talking about. And in order to get a sense of what happens broadly when such tournaments occur, we can't just do one simulation. We'll get, okay, I won 5 and you won 4. What do we make of that? I don't know. It doesn't really, I don't know what to make of that. We can't just make one simulation here in order to get a sense of the probability of things. We have to do this lots of times. And again, somewhat arbitrarily, I've just chosen the value 10,000. So this is what we have to do this thing 10,000 times. 10,000 is a pretty big number and it's good enough to get a sense of how things are going to fall out, but small enough that a computer can easily do it. So again, we're going to do the 9 coin flips and count the heads in order to resimulate one experiment, but we're going to repeat that act 10,000 times, and we're going to keep track of the outcomes, right? Because that's the point, keep track of outcomes. And what we're really doing here is we're producing a broad experience with what happens when two equally matched players will play chess. And most of these results are going to be 4s and 5s because it's out of 9 games and they're equally matched. So 4s and 5s will be the most common outcome. And 3s and 6s will be the next most common outcome. And 7 will occasionally happen. And so will 8 and 9, actually. But the point of this experiment is to assess how likely is it that 7 would actually happen if there were really just no skill disparity at all, if the players were equally matched, because that's what the p-value means. How likely are results like ours if in fact the null hypothesis is true? So I did this on the computer, and I resimulated the experiment, and I actually did it 10,000 times, as I said, and 903 times it worked out. So 903 results on the computer gave 7, 8, or 9 wins. So in other words, that tells you how likely it is, if the players are equally matched, that we would get evidence like ours or even more compelling, 7, 8, or 9. And so the probability then of results like ours under the null hypothesis is 903 over 10,000. And that's what the p-value means. It's the probability of results like ours if the null hypothesis were true. And that's 903 out of 10,000. And that is 0.09, or as a percentage, 9%. And that's actually, to my eyes, surprisingly high, right? And it's high effectively because the sample size was kind of small here, and that's really what's going on. So this is 9%, and what we're really saying here is, even if the players were equally matched, this kind of evidence would pop up accidentally about 9% of the time. And 9% of the time is, well, it's not all the time, but it's pretty common, right? It's not a very rare. It's not something that you would say, wow, I can't believe it, right? 9% is pretty common. And it's more common than our threshold of skepticism, what we technically call the threshold of significance. It's more common than this threshold of 5% of the time. So now we have to resolve this hypothesis, and we have to do the right thing next. What is the right thing to do when you calculate the p-value and you get, well, it's just not very surprising, right? Compared to our standard threshold, that's just not very surprising. Well, we do the opposite thing we did last time. Instead of saying the null hypothesis is absolutely incredible, I don't believe it anymore, it can't be a coincidence, we say the opposite. We say the null hypothesis is credible. This could be a coincidence. We don't actually have enough evidence. So let's summarize what we say here. We say H naught is credible. And we do not reject the null hypothesis. Now, where does that leave us? Does that mean the null hypothesis is true? Not really, because honestly, we played 9 games and I won 7. It's quite likely that I'm better. But we don't have statistically significant evidence of that claim, right? So we might call this preliminary evidence, or we might call this, weak evidence of the claim, but we do not call it statistically significant evidence. It is as yet undetermined to a significant degree that I am better at this game. But it's also incorrect to say we've proven that the players are equal. Obviously, this outcome can't prove that the players are equal at the game, but it hasn't proven that the players are unequal at the game. And so we kind of end with ignorance. So we don't know. And this is the frustrating conclusion of many statistical hypothesis tests. The conclusion is we don't know. Science needs to have the capacity to say more evidence is needed, right? This is the situation in which more evidence is needed, okay? Science is sometimes, a slam dunk, it's obvious, the conclusion is here. But sometimes we have a little bit of evidence and it isn't enough. And a proper humility requires that we sometimes say, gosh, I just don't yet know what the right answer is. So when we say we don't know, we mean that the alternative hypothesis is still credible. It could be. We mean that the null hypothesis is still credible. It could be that too, and we don't know. If we play these 7 games out of 9 and I win more, well, that is some evidence that I might possibly be better, but it's not enough evidence to say with a statistically significant degree that I am actually better. And the reason is because the p-value is bigger, more probable than our threshold. So that's 2 statistical tests carried out by means of simulation. In future videos, we'll see other techniques for carrying out and resolving these statistical tests, including the analysis of standard error.